In this next module, we're going to introduce a few more functional groups. So the next functional groups are known as ketones, and ketones are that carbon-carbon double bond, again, the carbonyl, and this time it's flanked on the left and flanked on the right by a carbon. That's different than the aldehydes, where aldehydes were carbon, carbon-oxygen double bond, hydrogen. Ketones are carbon, carbon-oxygen double bond, and another carbon, where again R and R prime could be the same, they could be different. Where R and R prime are any carbon length, they could be equal or they could be different. We're going to know that we're dealing with a ketone because of the name. It'll tell us within the name that the functional group we're dealing with is a ketone. Just like aldehydes, we had the Al ending. With ketones, we have the ONE ending, letting us know a ketone is present. And also, like the aldehydes, for these smaller structures, we'll have two names, the common name and the IUPAC name. I do not expect you to know all of the common names. We're going to practice the IUPAC nomenclature for the functional groups that we're covering today. So for example, a 3-carbon ketone, you commonly know it as acetone or nail polish remover, but if we had something that was 3 carbons long and it was an alkane, we would call it propane. Well, we drop that E ending and we add ONE, and it becomes propanone, where that ONE tells us that we have a ketone present. Because the ketone has to be flanked on the left and the right by a carbon, we will not find a ketone in anything under 3 carbons long, right? If I had 2 carbons there, this would be an aldehyde. This wouldn't be a ketone. And certainly if I had 1 carbon there, again, wouldn't be possible to make a ketone. So the smallest ketone we'll see will be propanone, also known as, or commonly known as, acetone. The next one up, now I have a 4-carbon chain, I would call that butane. But because I have a ketone present, right, I'm going to drop the E, and then I'm going to add ONE to that ending, and this would become butanone, where that ONE tells me that I have a ketone present. And in this case, to be more precise, we'll also number that, and we want to number that with the lowest number possible. So here's a ketone for you to try to name, remembering that we name the longest carbon chain, we drop the E ending and add ONE. So how would you name this ketone? Well, first, the longest carbon chain would be right here. It's 5 carbons long, so 5 carbons would be pentane. The ketone is on the 2nd carbon. I want to have the ketone to have the lowest number possible, so here's carbon 1, carbon 2, 3, 4, and 5. So to put that all together, right, we're going to drop the E ending from pentane, and we have to add ONE. So this would become 2-pentanone. The next group are carboxylic acids. Carboxylic acids are a little bit different in that we have our carbon, but now we have our carbonyl, carbon-oxygen double bond, and we're going to end with this carbon-oxygen hydrogen. That's going to make our carboxylic acids. Much like the aldehydes, you've probably come in contact with a carboxylic acid before. Lactic acid is an example, citric acid. Acetic acid would be another example, so acetic acid being the common name, ethanoic acid being the IUPAC name, because taking a look, we have a 2-carbon chain, so that would be ethane. We drop the E ending and add oic acid to let us know that ethanoic acid is a 2-carbon chain with a carboxylic acid functional group. You and I know it as acetic acid or vinegar. Even some pharmaceutical compounds that we take, like aspirin, also contain a carboxylic acid. So aspirin is also known as acetylsalicylic acid, indicating that we have a carboxylic acid present in that molecule. Acid nomenclature is pretty easy in that, like I said, we take the parent name of the hydrocarbon, we drop the E ending, and add oic acid. So here's an example of that, right? I've got a carbon chain that is 1, 2, 3, 4 carbons long. So 4 carbons long, that would be butane. I have to drop the E ending, and I have to add oic acid to that. So that would become butanoic acid. Esters are the next functional group that we're going to talk about. Esters are a derivative of a carboxylic acid in that we've replaced that terminal hydrogen now with another carbon chain. So the difference between a carboxylic acid and an ester is that a carboxylic acid, we had carbon, the carbonyl, and then oxygen and hydrogen. We've replaced that hydrogen now on a carboxylic acid with another carbon. So we have carbon, the carbonyl, oxygen, and then another carbon. So now we've gone back to the R and R prime, where R and R prime could be any carbon length. They could be 1 carbon, they could be 10 carbons long, they could be the same, they could be different. We name esters by first naming the carboxylic acid half of the ester. And so in this case, right, there would be our carboxylic acid half. That has 2 carbons in it, so that would be known as ethane. We drop the E ending and we add OATE, and so that would be ethanoate. So after we name the carboxylic acid half, and you can kind of see I color-coded that, the next step is we need to identify the alkyl group that is there. So what is attached to that ester? Well, in this case, I've got a 1 carbon alkyl group, so that would be methyl. So now putting that all together, the alkyl group is my prefix, so methyl, and then my ending, ethanoate, would be the name of this ester. So here's one more example. Let's name this ester. So step 1, I want to name the carboxylic acid half of the ester. I want to identify that half of the ester. So I have 1, 2, 3, 4 carbons. So 4 carbons would be butane. I'm going to drop the E ending and I'm going to add OATE. So that would become butanoate. That's the ending. The next, I want to identify the alkyl side. The alkyl side has 2 carbons in it, so that is ethyl. So now putting those both together, right? Ethyl butanoate. And whether you know it or not, you're familiar with ethyl butanoate because that is the aroma of pineapple. And so I just threw in a few other extra examples here. I wouldn't expect you to name these more complicated examples, but the one down here, for example, all the way on the left is geranyl ethanoate or geranyl acetate. Right, we know it as the smell of roses. The next one would be benzyl ethanoate. And that's the aroma that we would get from apples. And the last one, we actually made this in my undergraduate organic chemistry lab, is isopentyl ethanoate. And that is the aroma of bananas. So that's kind of like the artificial Laffy Taffy banana flavor banana aroma is isopenyl ethanoate. Again, though, we want to name these by what is the name of the carboxylic acid. So here's my carboxylic acid in all of these. All of these have a 2-carbon carboxylic acid. That's ethane. That would become ethanoate. And then after that, we want to name the rest of the molecule. What's the alkyl substituent that I have? Esters can be commonly hydrolyzed. So the example of the biodiesel lab that you did in general chemistry, you did the saponification reaction, which is basically you're adding water across that ester functional group to produce a fatty acid and glycerin. And that's used in the production of soap. You're taking a fat, a triglyceride, you're hydrolyzing it in under basic conditions. The ester functional group is easily prone to hydrolysis. So we're adding that hydroxyl group across, releasing 3 fatty acids and the glycerol molecule above. This would be very similar to the lab that you did where you did the production of biodiesel. You require the hydrolysis of a triglyceride to produce those fatty acids and the glycerin in that lab. The next group of functional groups are amines. Amines are known as, they're generally basic compounds, and also amines, we rather not work with amines because amines tend to have a fishy aroma. They tend to not really have a very nice aroma associated with them. We're not going to really focus too much on the nomenclature of amines, but as you can see, it's similar to other trends that we saw where if I had a 1-carbon hydrocarbon, right, that's methyl. Well, now I've added an amine to it, so that would be methylamine. Here I have 2 methyl groups, so that's dimethylamine. I have 3 methyl groups, that's trimethylamine. Or here I have an ethyl group, right, that would be ethylamine. All you really need to know at this point is how to identify an amine. To identify an amine, we are looking for a nitrogen functional group in that molecule. So nitrogen connected to a carbon or a hydrogen in that molecule. So here's a question for you. Try to identify as many functional groups as possible in this structure. This is a structure of HIV integrase inhibitor. And basically this drug, it basically prevents HIV from integrating its viral RNA into your genome. And that's how it hijacks your cell, is that HIV inserts its viral RNA and then it convinces your cells to make copies of that viral RNA. And so this drug, this HIV integrase inhibitor, inhibits the HIV's ability to insert its viral RNA into your genome. So how many functional groups can you identify? So to get us started, I've got 1 functional group over here that would be a carboxylic acid. I've got a 2nd functional group here. This would be a ketone. I've got a 3rd functional group here. This is a hydroxyl group, alcohol. I've got a 4th functional group here. This would be an amine. And a 5th functional group here. This would be an ether. We didn't talk about it, but they were listed in that chart. I'm not really going to expect you to know these, but these 2, you could call these are like a halide functional group or an alkyl halide functional group. They're halogens. Fluoride and chloride are both halogens, and they're attached to a carbon structure. But the main functional groups and the ones that you certainly should have been able to know are the carboxylic acid, the alcohol, the ketone, the amine, and the ether. So I'd be happy if you identified 5 functional groups in that structure.